Hey everyone, welcome back. We're going to be talking about trend lines in our scatter plots today. That's the main focus of what regression analysis is trying to plot in what that trend line looks like, so that then maybe we can kind of predict some information based on the plot we have and some values that we want to see what we should be expecting. So I'm going to start with some vocabulary. The least square regression line. That is a line that makes the sum of all the squared residuals as small as possible. It summarizes the relationship between the two quantitative variables if one of the variables helps predict the other. So that's what the line is going to do. It helps us with the thing. It kind of fills in with the correlation, so we can know how accurate our predictions are based on a correlation. But the least square regression line, to find those, is basically to take your actual values of y, figure out some sort of predicted value based on our regression line, and then sum that difference. And then all those values for all our y values, we're going to do that for every one, squaring them, and then add them all together. And we want that number to be as small as possible. So that's how we figure out where the least square regression line fits. It's a completely tedious process. It's not something you would ever want to do by hand. So what we do is use software. We'll use Google Sheets as we go through this part of the unit, to create what our regression lines are going to be, to help us with that part of our stuff. The predicted value is the value predicted for y based on the values of x from your regression line. So once we find out what the regression line is, we're going to go through and kind of figure out what would we expect our response variable to be, the response variable output to be based on certain values of x. The values of x we're going to use to predict that are values of x that fall within the range of our maximum and minimum value of x for the data that we've recorded. If we have relatively low values for x in all our data, we're not going to try to predict 100. What would happen if x was 100 for our response variable? Because that outcome would be completely unnecessary and completely ludicrous number sometimes when you kind of look at them. Slope, it's just like slope of y equals mx plus b. It's the amount y is going to change by every change in x. So as our x values go up, the y value will change accordingly. And then the y-intercept, its value you would expect to get for your data if x was 0. So if it's it's really only going to make sense a lot of times when you have really low values for x as your data. If we have really high values of x, then your y-intercept, isn't really going to give you much good useful information from what we're looking at compared to when the x values are low. So that's our vocabulary. We're going to move on now. The regression line, like we said, it's a statistical equation. It's very, very similar to the slope of a line, the slope-intercept equation, y equals mx plus b. They just kind of flipped it so the slope and the x go to the end of our equation rather than the beginning. And then rather m and b for our intercept and our slope, we're actually using a and b. So to help, we're going to define our variables so we know what they mean. Y hat, that's actually red y hat, is the predicted response value. So that's going to be our y value of our data or our prediction when we plug something in for x. A is the y-intercept, so it would not be anymore. The y-intercept now is a for our statistical regression line. Our slope is b, and then the explanatory variable, the x, is the variable that we're using to help predict what we're looking for. That makes sense? Pretty simple, pretty easy. Okay, so we need the value of the y-intercept to draw the line, but it is only statistically meaningful, like I said, when the explanatory variable takes on values close to 0. So if your minimum x value is 120, the y-intercept really isn't going to mean anything for you in a statistical sense. You need to have your values close to 0. The regression line can be used to predict the response variable. So we're going to get our y value. The response variable is what we're looking to study. For every for a specific value of our explanatory variable. So if you have your range of x variables, you might not have a prediction or an expectation of what it would be if it was like 75, which is in our range. Then it would plug 75 into our regression line, our trend line equation, to figure out what we would expect that value to be. It should kind of always fit in with what the data is looking like in our scatter plot. We don't want to go way outside. Doesn't make sense to do predictions, like I said, when the values of x are way outside our range, because they're getting farther and farther from our line, kind of. This line, the regression line, doesn't really extend on forever. It's more just fits within our data. When you do that, it's called extrapolation. It's a really bad way to forecast and guess things, and sometimes your numbers will be really far off. So it's a way to kind of, what we're looking to do is we've recorded a lot of data a lot of times. We have a regression line now from all the data we've done. And then what we're looking to do is say, okay, we're going to make a prediction based on a certain value of x. And then you're going to go out and rerun your experiment or your observation and do something at that value of x to see what you get for a response, and to kind of see how good you are with a prediction. The higher the correlation number, so the closer the correlation coefficient is to 1 or -1 in our examples in our stuff, the stronger that response is going to be. So then the line of best fit actually is pretty accurate with what we're trying to do. So that's kind of what the rest of that thing says. And there is always one point that goes through the regression line, and that's the point where the x mean the average of the x and the average of the y. Once you find the averages of x and y, your line of best fit is going to go through that point, and then it's just kind of the pivot for where do I kind of make the line look the best as we're putting to it. If you ever wanted to do one by hand, it's like, where does it look best to kind of do it. And like if you're doing it by hand, what you're trying to do is you get a straight edge, go through that point where the average is, and then you're trying to get the line so that half of your scatter plot dots are above the line and half of them are below. That's the best way to do it. So I'm going to run through an example. Again, like I said, it's the age versus hours of sleep. We're given our data. We're asked to create a regression line. I did that in the other video that you'll watch after this presentation, so you can see where it comes from. But our regression line actually is this, based on this data. It's hours of sleep equals 10.226 plus or minus 0.085x. What they always talk about, and what we've always talked about in stats, is our numbers in context. So rather than using y and x to put your regression line in context, you change out the y and x for what they represent. So our response variable in this example is hours of sleep, because we're using age to predict that. So our regression line in context then is hours of sleep equals 10.226 minus 0.085 times an age. So does that make sense? Okay. So identify the slope of the regression line. Our slope is our b value. So the slope in this instance is the negative 0.085. It's negative because it's minus. The y-intercept in our example here is 10.226. Again, this kind of makes a little bit of sense, because you would expect the baby to sleep a lot of hours. I know babies sleep more than 10 hours, but it does kind of fall in line with what you would expect a younger child to need sleep-wise. And then we're asked to predict the number of hours of sleep for a person who's 49 years old and to show our work. So we're going to take our regression line and we're going to plug in 49 for our x value. So we're going to have y hat is going to equal 10.226, or hours of sleep, let's say, is going to equal 10.226 minus 0.085 times 49. You plug that into a calculator and you come out and you get a 49-year-old person should sleep 6.061 hours, or 6 hours. So somebody who's 49 years old should be getting, or it does get, about 6 hours of sleep. I hope that makes sense. It's a little short, sweet presentation today. You're going to have some extra classwork, which is going to be working on all the scatter plots we had done a couple weeks ago um, in the Google Slide presentation. What you're actually going to go back and do now is use that same data um, and create regression lines in the charts um, and kind of get those equations, and then you're going to report the equations back to me. Is what you're going to actually turn in for the assignment. So that'll be out on Classroom as well. Hope everybody has a good weekend, and I will see you all on Monday.